Good morning. First of all, it's a privilege to be part of this morning, and I really appreciate the opportunity. I'm going to caveat what I'm going to say here by what I heard in the last talk. The little bit I know. Because one of the things that is obvious to me in my years of working on the Great Lakes is that you never really truly understand what's going on. You have perspectives and you work from those, and then they change, and you are on to the next. If I can make it work. Okay, there we go. In my job, I've been very fortunate to have responsibility for going around the shores of the Great Lakes and taking a look at what the natural conditions, what the development, what the people are doing, and trying to assess how that affects water quality as part of an effort to, I guess, understand and protect water quality. A few years back, I had the opportunity to do this in eastern Georgian Bay. This presentation this morning is really about some of the things I learned during that experience. It starts with sort of one very stark observation. There are really two types of water in eastern Georgian Bay. There's the blue water, which is affected by the conditions in Lake Huron. It's the Lake Huron water. And then there's the brown water, which is the water that comes off the Canadian Shield, the rivers that drain into the coastline. This presentation, I'm going to try to do two things. First, just describe the differences in the two types of water. Then, explain a little bit how they mix on the coastline, because that really sets the stage for a lot of things. But the real message is here is to really talk about how those two types of water and their interaction sets and defines the aquatic environment of the coastline. This beautiful stretch of coastline that is so appealing and so enthralling. The blue water. The blue water is very distinctive. It's really a creation of the geology of Lake Huron, which is this old sedimentary rock. It's very calcareous, and so it creates a hard water. It's rich in calcium, an alkaline pH, but it also has another feature which is really stark. It's got very, very low levels of phosphorus. Very unproductive. It's not a great place to grow lots of plants. It's kind of almost desert-like in some ways. It's high transparency. It's very clear water, and there's not much in it in terms of particular material or color. Now I've got three arrows here on the figure. Calcium 24. It's moderate level, but it's the phosphorus I'm going to draw attention to. It's 2 micrograms per liter. Anybody who works with water chemistry realize that is what they call ultra-oligotropic, extremely nutrient rich. And this is from last year down around Collingwood. It's pretty much characteristic of the outer coastline here. DOC is the next one, and that's the dissolved organic material. That's the brown staining. Think of it as putting a tea bag in water. It is the stuff, it is the soil, it is the broken down plant material that leaches into the water and gives it its brown color. The DOC level here is about 2, and that's typical of very clear waters, around the Great Lakes. Now, brown water, a horse of a different color. It's very much shaped by the geology of the Canadian Shield. And that is a hard rock with low levels of carbonate. So It's not got a whole lot of calcium in it. It's more acidic, and it also has this brown coloring, this organic material that's leached out of the soils and the plants. Now, what is distinct about it, though, it has a lot more phosphorus, so it's a lot more productive than the open lake. For example, now look at my 3 arrows, look at the calcium, it's about half of the open lake, but the phosphorus is now 9, almost 10, that's 5 times higher than what's out in the open lake. The DOC is also about double of what's in the open lake. So it's a very different water. Now, for me, when I sort of started working with this stuff, it was very helpful to envisage the coastline as a band, as a coastal band, where you have these 2 extremes, these 2 types of water mixing from one end and the other end, coming together, creating this diversity of conditions that is really shaped by the different nature of the water. Now, unfortunately, this is a necessity in sort of looking at coastal water quality is some appreciation of mixing, how water circulates. Water is, yes, it's always moving, but it has certain features that help understand how the land, the water leaving the land will interact with the water on the shores of the lake. And in this regard, Eastern Georgia Bay is very distinctive and different than much of the Great Lakes. Now, in much of the Great Lakes, we have a predominance of flow back and forth the shoreline called along-shore flow. And if you look up at the, way up at the top left here, I've got along shore. Basically, water moves one way along the shoreline, back the other way along the shoreline, and it dilutes the land runoff in different directions on the order of about 2 to 5 days. And so there's never really strong gradients in water quality set up. So it's highly variable, and it is distinctly different than what we have in a lot of places on the coastline, which I call estuarine-like. Estuarine-like in the sense that water is passing through almost quasi-channels from the land out to the open lake, and it's moving back. It's still moving back and forth because the river forces it out, the discharge from the rivers force it out, and the lake pushing, the wind driving the lake pushes it in. So it moves up, moves back, and depending on where you are, you get more lake influence or less lake influence, and it varies over time. These arrows, I should have said off the top, these are current meters, instruments measuring the flow of the water. And this is a year's, about 6 months of data daily showing the general progression of water movement back and forth at points where these meters are located. Continuing flow, there's a strong seasonality in the flow. Now, I guess the premise here is the rivers drive the water out, the lake drives it in. So if you have strong differences in the discharges from the rivers, the patterns, the mixing of the water in along the coastline is going to vary seasonally. Now this is discharge from the lower part of the Moon River. And what you see here is that you got a lot of water coming out in the spring and early summer, not very much coming out during the summer, and then again in the fall, the discharge increases. Again, this is many, a number of years. It's a pretty thing. So the implication here is the mixing across the shoreline. The rivers have stronger, a much stronger influence in the spring, so you see more river water in the spring, and then conversely during the summer, the lake pushes much more strongly into the coastline and further up the rivers when the flow from the rivers are small. And what this means is that water quality, when you look at water quality, you look at the water, it doesn't matter if you measure it or just look at it, if you're in certain parts of the coastline, it's going to look different from spring to summer. It's going to look different as the rivers change, the rivers change the amount pushed out and, depending on how much wind's out in the lake and how much is pushing in. Now, okay, what I really want to do is in this presentation was talk about how these two types of waters define what I call the aquatic environment. And the way I'm going to approach it here is look at the features that we consider as part of the aquatic environment. What is it that defines the aquatic environment? I think I got 5 of them listed here. And I'm going to go through each and sort of show how the interaction of the two types of water varies and comes together to shape what is this complex and diverse environment out there. Okay, exposure. Anybody who goes out on the lake knows that, you know, there's a lot more energy, lake energy, if you're out of the outer coastline compared to whether you're in the embayments in the inner coastline. The implications of that for water quality and biology and things that live are tremendous. And I just want to sort of develop this idea a little bit. There is this consistent gradient across the coastline, or what I call the coastal band. And I'm demonstrating this here by measurements of fetch, just how much openness there is to the water as a function of moving away from the shoreline. If you take the shoreline reference line here, this is up around Schwanaga, and you move out away from that line into the lake, exposure increases as identified by the fetch. Now, one of the implications here I wanted to demonstrate is the fact that the nature of the bottom of the lake changes as you move onshore to inshore as a function of this. Out on the outer coastline, it's all rock bottom. It's sort of rocks. It's very exposed rocks. You get midway into the coastline. Now the bottom is all depositional sediments. And that's, it doesn't matter where you go up and down the coast, it's the same thing. The implication here for biology and for organisms is tremendous, because now you have two different types of animals that are going to, plants and animals that are going to be living in different parts of the coastline. Another example of exposure is important is water mixing, the lake mixing, and how it heats, and how it delivers, basically circulates internally. I've got the Moon River here. I've got a location on the outer Moon River, a location on the inner Moon River, where you have a very radical difference in what we would call lake stratification. So this is water temperature through the water column over a spring to fall period. Now, in the case of the inshore location, that's the inner part of the coastal band, you've got this characteristic gradual warming of the water column. The water column is structured. The top of the water column doesn't interact with the bottom of the water column. It's a typical inland lake kind of situation. You go out into the more exposed areas, you've got a situation where it's much more energetic. The water column is mixing, so the bottom water is moving up, the top water is moving down, and it circulates nutrients, it controls the way in which organisms are able to live there differently than in the inner part. So there's this sort of physical underpinning that varies. In addition to that, the inner parts of the coastline typically have warmer water than the outer parts of the coastline, because you're delivering periodically this cold water from the depth up to the surface, because the physical agitation of the water column because of the exposure. Light. Light is a really important feature of aquatic ecosystems, and there is a drastic contrast between the brown and the blue water. And it will affect just about everything across the board in terms of the organisms that are living out there. The brown water does not let light get through. The blue water does, and I'm going to show you an implication of that here. These are what we call light attenuation profiles. We do, in our monitoring, we do a lot of light measurement for this purpose. And so all you're really looking at is light measurements going down through the water column, and the light decreases. Now, light here is measured as PAR. PAR is that wavelength portion of sunlight that plants can use. And we have two situations. We have a blue water and a brown water. One of the measures we often use to quantify this is what we call photic depth. Photic depth is 1% of the surface light, and is generally taken to be the point at which you go from having enough light for plants to grow to not enough light. So basically, I compare the two here. In the blue water, the photic depth is 30 meters. The site is actually 20 meters, so that means there's enough light throughout the water column right down to the bottom of the lake to grow plants. You look at the brown water, now our photic depth is 9 meters. So below 9 meters depth, there's not enough light for photosynthesis, for phytoplankton. If you look at the bottom of the lake, the bottom of that site, which is 15 meters depth, there's no light. So basically there's nothing growing on the bottom of the lake. And if you go across the coastline, there's this dichotomy between the types of areas where you have light, sufficient light on the bottom of the lake versus not on the lake, not enough light at the bottom, and the implications for the growth of algae and things that rely on the growth of algae is tremendous. Okay, nutrients. Now this is what we gravitate to usually in terms of water quality. We'll talk about nutrients. Anyway, the message here for nutrients on the coastal band is that you can't easily define what the conditions are. There isn't. What I've shown here is measures of what we call trophic stats, a level of productivity, and it's based on criteria that are used around the Great Lakes in terms of spring total phosphorus and chlorophyll A concentrations during the summer. What I've done is a number of services, I've just sort of thrown them all together, and because a lot of the work we do is spatially broad, we can do it on the basis of the area. And so percentage of the areas falling into 4 trophic categories. And what I want you to see is the fact that the ranges are quite broad, within categories, and that there are, the conditions expands right from ultra oligotrophic to eutrophic. Mostly oligotrophic and ultra oligotrophic. But the point really is that because of the mixing of these two types of water, different contrasting nutrient regimes, there is no easy way of describing it. It depends on where you are and what the conditions are. Now, I want to delve into this a little bit further to kind of make the story a little clearer here. Let's just start off with this one here, which is really making the point that the rivers, the delivery of phosphorus from the rivers drives the machine. And the plots here are simply a phosphorus concentration plotted against dissolved organic carbon concentration, with dissolved organic carbon concentration being that representation of the P of the breakdown. What's happening here is drainage from the soils, the breakdown of materials in the watersheds. It's being focused into the rivers, out into the coastline. Now, I missed one here. I jumped up a little bit, but please forgive. Okay, I wanted to start off with productivity, showing you, the link between the phosphorus and the productivity. Okay, here's a map of chlorophyll again, the Moon River. Chlorophyll is a representation of the nutrient richness and the productivity. It's a heat map, so what you're looking at is high concentrations of chlorophyll in the bay areas, the inner part of the coastline. Blue, very, very low levels of chlorophyll. So there's this gradient from onshore. And this gradient is ubiquitous across the coastline. You can go anywhere you want and you'll find it, given the nature of the coastline. So basically, I'm just showing cog machine and go home here just to sort of back up this point. This, and again, you've got the color scaling, but it's not consistent in time because it varies as the amounts of water, entering the system from the rivers changes. Now, I did this one, and this takes us to this one here, which is really, I guess, the one that's probably quite important for the nutrient story. What I'm showing is DOC concentration, and it's a map, the same thing. High DOC, low DOC, offshore is what I've been saying. But here I've got phosphorus concentration, and I've got it mapped as distance offshore. So here's the reference line. So this is on the x-axis, this is distance offshore. You see this drop in phosphorus concentration from onshore to offshore. And again, you can go up and down the coastline, and that's a characteristic feature of the coastline. And it's driven by the rivers. Now, okay, changing gears onto the next feature. This feature of water quality in Eastern Georgian Bay often is overlooked, but it's extremely important. And that's the base chemistry. It's about the calcium, it's about the hardness of the water, it's about the pH of the water. Most types of organisms have adapted, have evolved to use or prefer limited ranges of calcium, pH, and alkalinity. And that's because of the importance of ions and the physiological and biochemical functioning of plants. So there are different regimes that most types of plants will vary, and it's a function of how they've evolved and what geologies they've evolved in. Now, when you look at the gradient of calcium in Eastern Georgian Bay and the gradient in pH and alkalinity, what you realize is that range spans a lot of the kinds of changeovers, preference that a lot of types of organisms, aquatic organisms, let me say it another way. The range and condition in base water chemistry is in a range that's expected to affect the distribution and the success of a number of species of organisms, period. Now, I'm demonstrating the gradient here using, that's a map of conductivity. Conductivity is a measure of how much water will transport or how it will conduct electricity. It can be measured out in the field easily, reliably, no problem. It is, in Eastern Georgian Bay, it's a great way of looking at calcium. Calcium is the major ion in the water, and calcium concentration sort of varies very, very strongly, predictably with specific conductivity. So the map over there, think of it as a calcium map. So you've got, in the inner parts of the coastline, you've got low calcium, in the outer parts, high calcium. And this is again because of this interaction between the blue and the brown. The brown water does not have it. It's very low in calcium. Now where that one, I wanted to I'm going to finish off here with just a couple of examples of where that's important. But and this is one of the areas where I think I'm just scratching the surface here in terms of the significance of it. If you were to start looking at the distribution of organisms and where and why they are in different parts of the coastline. Oh man, changes too fast for my. Okay. Here's a very real example of where this matters. And it's not just an organism, it is well, having worked all around the Great Lakes for many years and tracked this, it is a monster. And this is the dracaenic mussel, the zebra and the quagga mussels. In Eastern Georgian Bay, it appears that the inner parts of the coastline do not have sufficient calcium to support dracaenic mussels, which is in fact a big win here. And I'm demonstrating this here with some work that we did a couple of years back. Now, I've got the conductivity map again. The blue line now is that sort of barrier between muscles and no muscles, which is about 140 microsiemens per centimeter, or 15 milligrams of calcium. So inside the blue line, no muscles or very few. Outside, muscles. So what it means is up and down the coastline, there are lots of areas where you're protected from mussels, which have very destructive, potentially very destructive effects on substrate, on certain types of organisms, and are linked in many areas with the proliferation of nuisance algae and algal-related problems. So that's a very real one, and no question about that. Here's something I'm just finishing up now in terms of, hopefully before I finish up here, that gets to the same thing in a more diverse. This is really a prompt for me. I don't expect you to understand this, but basically we've done a lot of surveys looking at what we call benthic invertebrates. These are the animals, the small animals, the worms, the snails, the amphipods, the little critters in the mud. For decades, Great Lakes people have looked at the composition of the benthic invertebrates and used it as sort of an indicator of ecosystem condition, nutrient enrichment problems of various sorts. Basically, a biological feature that has a lot of information. And we were using that, really kind of looking at the coastline in terms of where there might be problems, enrichment problems, and the like. What I found is that the strongest influence on composition, again, is this coastal gradient, the brown to the green. It is the thing that steps out first in terms of, there's a segregation of assemblages of species that seems to be related. Now, whether it's related to base chemistry, exposure, or nutrient enrichment, or whatever, I'm not exactly sure, but it is consistent with this notion that the aquatic environment fundamentally varies between the brown and the blue water, and the organisms follow suit with that gradient in conditions. Now, I had a slide here, but I was worried about time on gobies. I think the same thing happens with the round goby as happens with the seeded mussels, again, leading to this notion that the inner coastline is protected by low calcium, ironically, and which is probably a bit of a good news story. So let's summarize here. There are these gradients in conditions, and they're pervasive up and down the coastline, on top of anything that may also be happening due to development and pressure in the lake. But this is what stands out. This is what I learned. But the gradient likely exerts a strong selection pressure on the aquatic plants and animals of coastline in eastern Georgian Bay. Okay, I think my colleagues and their field crews worked hard on this work. Claire Holm is a colleague of mine who also worked on this. And certainly I have to acknowledge University of Toronto, Matthew Wells, and Leshika for help on the lake circulation side. And Polytech out of Sarnia were the man to help for a number of the diving service. Okay.
Thank you.
We have time for 2 questions. Oh, we're so hot and off. Way to go, Rupert. Fire away.
Easy one. Have you been able to incorporate the impacts of climate change? I'm thinking this end particularly more severe storms, and warmer water. Are these things happening yet?
Not from what we've done, but to reassure you, it's top of mind in terms of the work that we're doing in Great Lakes in general. And unfortunately, most of it at the present time is site in southern Ontario. But during the course, we were, the combination of stuff, periodic stuff and more intensive, there's just not enough to be able to get at that at this point. But yeah, it very much is a necessity going forward to try to ascertain where that's going to take us.
One more? Cool. I'll let it take it.
Yeah, when I was looking at your numbers, it wasn't clear whether human activity is driving any of this, or if this is just natural and that's because we're shield in open water.
Well, okay, the answer to that one, I need to be a bit careful because I have been unable to find, at least in the areas that we've been, very clear signals of anthropogenic effects that can be extracted from the natural. The problem from a monitoring and from a sort of a management perspective that exists on the coastline is that the natural variability is so strong that it is going to be quite challenging to detect that anthropogenic signal, and so you really have to start putting on a different hat in terms of how you go about business and looking at other types of indicators and other kinds of measurements to pick out that anthropogenic influence because it's varied. And I've tried to pull it out, and frankly, I've had a hard time doing it.
So Todd, thank you very much. And there is from a hive outside of our office here, your sound, honey. And I just wanted to give a round of applause to both of our speakers on water, Wab and Todd's, and Chi Miigwech for the perspective. And thank you.